Now, a little bit about Mike Clancy. Mike earned a BS in oceanography from Florida Institute of Technology in 1973 and an MS in meteorology from the University of Miami in 1975. He joined the U.S. Navy's Fleet Numerical Meteorology and Oceanography Center, and there's an acronym for that. It's FNMOC. That's Fleet Numerical Meteorology and Oceanography Center. That's in Monterey in 1983, and was selected as Technical and Scientific Director of FNMOC in August of 2005. Mr. Clancy authored over 100 publications in meteorology, oceanography, and information technology, and received over 50 professional awards, including the Navy's highest civilian award, and prior to his retirement from the federal service in 2011. He was inducted into the FNMOC Hall of Fame in 2015. Mr. Clancy is a member of the Monterey chapter of the Citizens Climate Lobby, which has an acronym of CCL, and he is a frequent speaker on climate change. So please let us welcome, put our hands together and clap for Mike Clancy. Thank you.
Thank you so much, Carol, for that introduction. I want to thank Carol and Don McDougall for setting this up for me. I'm a big fan of Point Lobos. I love the place, and I'm a big fan of the Point Lobos docents. You guys do a great job, provide a wonderful service down there. So I'm thrilled to be talking to you today. Now I'm going to share my screen and bring up my talk. So let's see here. Now you can play around with the view here, and I think you can probably keep both my slides on the screen and me on the screen at the same time. It's most important that you see my slides, so make sure that you don't have anything that's obscuring the slides here. First of all, let me ask everyone to mute their microphones so we don't have background noise. But if you have a question, please unmute and stop me. I have to tell you, I tend to talk very fast. I'm going to be covering a lot of material. I'm going to be showing you a lot of technical material. If it doesn't make sense to you, if you don't understand what I'm showing you, please unmute and stop me, and so I can explain. So let's jump right in here with taking a look at an outline of the talk. We'll start with introduction and context, get into the greenhouse effect, talk about greenhouse gases, look at global warming projections for the end of the century, talk about the global consequences and the local consequences right here in Monterey County, a brief discussion of what needs to be done, closing comments, and hopefully there'll be time for discussion and questions at the end. So introduction and context. What we're showing here is global mean surface temperature of the Earth for the past 5 million years. So this is global mean surface temperature of the Earth in degrees centigrade, and this is time going backwards back 5 million years. Global mean implies averaged over the entire face of the Earth, North Pole, South Pole, all around. Surface temperature over the ocean means the sea surface temperature over the land and over the ice covered areas. It's the temperature a couple of meters above the surface. What we see here is that beginning with the Pleistocene epoch, about 2.5 million years ago, the Earth entered into the Ice Age cycles. For the first 40,000 years, for the first 1.5 million years, the Ice Age cycle was a 40,000 year cycle. And for the last million years of the Pleistocene epoch, we've been in a 100,000 year Ice Age cycle. Now I'm using the term Ice Age to indicate these downward excursions, which are technically referred to as glacial periods. That's periods of time where the continents were covered by glaciers. And the upward excursions here are called technically interglacial periods, but I'm going to use the popular term Ice Age to represent these downward excursions of temperature here. So why am I talking about Ice Ages in the Ice Age cycle? We're here to talk about climate change. Well, the climate change we're concerned with occurs against the backdrop of natural climate change. And for the past couple million years, the ice age cycle has dominated natural climate change. So we need to understand the ice age cycle so we can separate out the human-induced climate change that we are concerned with. So the question on the table is, do we understand the ice age cycle, or is it just some big mystery to us? It goes up, it goes down, we don't know what's going on. Well, the answer is we absolutely do understand the ice age cycle. And in fact, we've understood it for about 100 years. The ice age cycle is driven by variations in the Earth's orbit around the sun and variations in the orientation of the Earth in space. That's what drives the ice age cycle. Now, I'm sure you all know that the Earth orbits the sun in an ellipse, such that in northern hemisphere summer, the Earth is farther away from the sun than it is in northern hemisphere winter. That's good for us living in the northern hemisphere because it makes our summers a little cooler and our winters a little bit warmer. What you probably may not know is that this ellipse is not constant in time. It actually changes on a 100,000 year period due to the gravitational force of Jupiter and Saturn acting on the Earth, such that there are periods of time when it's more elongated, like an ellipse, and there are periods of time when it's less elongated, more like a circle. Now, this figure here is exaggerated. It's actually only about a 1% variation, but that 1% variation in this ellipse here is enough to have a profound impact on climate. I'm sure also that you know that the Earth's axis is inclined relative to the plane that the Earth orbits the sun in. Of course, that's what gives us the seasons. In northern hemisphere summer, the North Pole is tilted towards the sun. In northern hemisphere winter, the North Pole is tilted away from the sun. But what you may not know is that that tilt does not remain constant in time. In fact, it fluctuates with a 41,000 year period due to the gravitational force of the sun and the moon acting on the Earth, and the fact that the Earth is top heavy. The Earth is not a perfect sphere in terms of its mass distribution. There's a lot more land in the northern hemisphere than in the southern hemisphere, so the Earth is top heavy, and it rocks back and forth on a 41,000 year cycle here. And finally, I'm sure you know that there's a North Star, that the North Pole points to the North Star. That star is Polaris. But what you may not know is the Earth wobbles. And again, it has to do with the fact that the Earth is top heavy. And as a result of the sun and the moon acting on the Earth with gravity, the Earth wobbles in a 27,000 year cycle, such that 13,500 years from now, Vega will be the North Star. And then another 13,500 years after that, we'll be back to Polaris being the North Star. Now, collectively, these are referred to as the Milankovitch cycles. You can Google that and read all about it, named after the famous Serbian astronomer and geophysicist Milutin Milankovitch, who figured this out and wrote it up back in the 1920s. So we've understood this for about 100 years, and it works like this. When these orbital variations conspire to decrease solar radiation striking the Earth during the northern hemisphere summer, that takes us into an ice age. Now, the cooling is amplified by 3 feedback effects that we'll talk about in a little more detail later. The most important one is the snow ice feedback effect. And what happens here is, as the temperatures are going down, that increases the snow and ice, and the snow and ice reflects more solar radiation away from the Earth, which makes the Earth cool even more. And you go around this feedback loop, and it amplifies the cooling. Water vapor feedback, as the Earth is warming, or say as the Earth is cooling, that decreases evaporation of water from the oceans and land. That yields decreasing water vapor in the atmosphere, so the atmosphere becomes less humid. And water vapor traps heat, it turns out, we'll learn later. And as a result, that amplifies the cooling. Similar effect with CO2. As the Earth is cooling, more CO2 is absorbed in the oceans. That takes CO2 out of the atmosphere. CO2 is an important greenhouse gas, so that actually increases the cooling. So again, you go around this feedback loop, and then amplifies the cooling as we head towards an ice age. Works in the opposite direction. As the Earth is warm, as these orbital variations conspire to increase solar radiation striking the Earth during the northern hemisphere summer, you go around these feedback loops in the opposite direction, and it amplifies the warming, and that yields a recovery from the ice age. Now, why am I talking about northern hemisphere summer? Well, it's because, why isn't southern hemisphere summer? Northern hemisphere summer, because the snow ice feedback effect operates much more strongly in the northern hemisphere than the southern hemisphere. That's because there's a lot more land in the northern hemisphere, a lot more snow on the ground, but also there's an Arctic Ocean. And when the ice in the Arctic Ocean melts, it leaves behind dark ocean, which absorbs solar radiation, and that really amplifies the warming effect. In the southern hemisphere, you've got Antarctica, and you don't get as strong an effect. So back to the plot here of 5 million years. Now I'm going to zoom in now way over here to the last 22,000 years, and that looks like this. Again, we're looking at the same parameter, global mean surface temperature of the Earth in degrees centigrade here, but now we're going back 22,000 years to the current time. And what we see here, this is the last ice age right here. And this warming period right here is the recovery from the last ice age, driven by the eccentricity cycle we just learned about. So what was happening here is the Earth's orbit was becoming less like an ellipse and more like a circle. And the Earth was drawing closer to the sun in northern hemisphere summer. And that was causing the Earth to warm and take us out of the ice age. Then we see this slow cooling trend, which was in fact driven by the obliquity cycle. So what's happening here is been happening for the last, 8,000 years, is that the Earth has been losing tilt. In fact, it's lost about 0.7 of a degree of angular tilt over the last 8,000 years or so. By the way, for point of reference, this marks the beginning of human civilization about 9,000 years ago. So right about here, this is called the Holocene warm period. All of human civilization has occurred in this period right here. And you can see there, the climate has actually been remarkably stable, slow cooling trend driven by the obliquity cycle, headed towards the next ice age in about 18,000 years. About 8,000 years, under normal circumstances, about 8,000 years from now, the temperature would start to really cool rapidly. It would take about 10,000 years to go into the ice age. And then we would be in the ice age for about 60,000 years, about 10,000 years to come out of it. We'd be in a warm period for about 20,000 years, and then another 10,000 years to go back into the ice age cycle. That's the 100,000 year ice age cycle. Now, there's a couple other things that show up here. This brief period of interruption of the warming is called the Younger and Older Dryas period. Dryas is a type of flower that they find in Europe during this period. This was driven by the melting of the glaciers on the Earth, lots of fresh water going out of the ocean, changing the ocean circulation. This is called the medieval warm period. This is a period, I think it was from 900 to 1200 AD, where the Earth was anomalously or slightly warmer. That was driven by the sun. The sun was actually, there was an increase in sunspot activity during that period. The sun was burning warmer. There's also a minimal period of volcanic activity, so less volcanic aerosols in the atmosphere, more solar heating of the Earth. So we had this warming period, followed by the Little Ice Age. Happened sort of in the time of Elizabethan England. This is a period of time, most famously, the River Thames froze over. It wasn't really an ice age. But again, that was sort of the opposite effect of the medieval warm period. The sunspot activity was at a minimum here, so the sun was burning less bright. And also there was a lot of volcanic activity, a lot of aerosols in the atmosphere, which reflected the sun and solar radiation away. And then finally, we come to this red spike. This red spike at the end of the record here, in fact, is the post-industrial global warming that we are concerned about. Now, there are two things that are immediately obvious in this chart. First of all, the warming we're concerned about, the global warming we're concerned with, is going in the wrong direction. The Earth should be cooling because of this obliquity cycle. We should be headed towards the next ice age, but suddenly we're warming, and we're warming very rapidly. In fact, we're warming about 20 times too fast, 20 times faster than natural climate change. The global warming of the past 100 years has been about 20 times faster than natural climate change, and in the opposite direction. So what does 20 times too fast in the opposite direction mean? Well, imagine you're a golfer and you're playing golf at Quail Lodge, and unfortunately, you take a wrong turn in your golf cart and you find yourself westbound on Carmel Valley Road. And unfortunately, it's car week. And suddenly you encounter a Lamborghini going the other direction at 200 miles an hour. Now, let me assure you, Lamborghinis can go 200 miles an hour, and occasionally they do go 200 miles an hour on Carmel Valley Road when there's no cops around during car week. So this is not that far-fetched. But the point is, if natural climate change is happening at the speed of the golf cart, what we've been seeing for the past 100 years is the Lamborghini going the other direction. So you should never confuse global warming that we've been seeing with natural climate change. 20 times too fast and in the opposite direction. Now we're going to zoom in once again. Again, we're looking at the same parameter, global mean surface temperature of the Earth, but now we're looking from 1850 to 2017 from 5 different sources, and they're listed here. Now, some of these sources, these are 5 independent groups, 5 independent data sets. Some of them use only in situ data. In situ data is data that's taken in place. It's like a temperature, it's measured, at a weather station, or temperature that a ship measures out on the ocean. And some of them use in situ data plus computer models, plus satellite data in a very sophisticated, what's called a data assimilation cycle. I won't go into those details, but the point is these 5 independent groups using 5 independent approaches all basically paint the same picture. And the picture is as follows. From 1850 to 1880, not much changing, slight decline from 1880 to 1910, pretty strong rapid upward movement from 1910 to 1945, slight decline from 45 to 75. And then beginning in the mid 70s and continue on to the current time, very strong rapid upward movement of the Earth's temperature, such that we're now running about 1.2 degrees centigrade above the pre-industrial level. Now note that the temperature doesn't go up in a straight line. Notice all these zigs and zags here. The temperature doesn't go up in a straight line. It's kind of like the stock market. There's volatility, it goes up and down. So what's going on here? Well, that leads us to talk about the difference between weather, climate variability, and climate change. There's 3 broad classes of phenomena in the atmosphere: weather, climate variability, and climate change. And the thing that differentiates these 3 classes of variability of phenomena are increasing time scale and space scale, going in this direction. So what does that mean? Time scale is just a fancy way of saying lifetime of a phenomena. Space scale is just a fancy way of saying the size of phenomena, or at least the domain of influence of the phenomena. On the left-hand side, we have weather, which runs from minutes to months in time, and about 10 kilometers to about 1,000 kilometers in space. And of course, that includes things we're familiar with: thunderstorms, squall lines, tropical storms and hurricanes, winter storms, blocking patterns in the jet stream out here in the month time frame. In the middle category, we have climate variability. And again, that's things that we are familiar with here. That would be El Nino, La Nina, taken together, that's ENSO, the El Nino Southern Oscillation, but also things like the Indian Ocean Dipole, which is sort of the Indian Ocean equivalent of El Nino, the Pacific Decadal Oscillation, which had an impact on the collapse of the fisheries in Cannery Row, the Atlantic Multi-Decadal Oscillation has an impact on Atlantic hurricanes. Climate variability occurs from months to decades, and on timescales about the size of the Pacific Ocean, or an ocean basin, about 10,000 kilometers. And finally, to the right, we have climate change, and that includes global warming, increase in currents of severe weather, non-cyclical trends in rainfall, et cetera, occurring on space scales of several decades to centuries to millennia, and it is a global phenomenon. So an important sort of rule of thumb here is, if someone is showing you a record that's 20 years or less, you're not looking at climate change. You're in this middle zone here. You're looking at climate variability. You're looking at things like El Nino and La Nina and that sort of thing. To be confident you're looking at climate change, you really need to be looking at a record that's 30 years or longer. And it should be a record that's global, because climate change is a global phenomenon. 20 to 30 years is kind of gray area, but really you really want to be assessing climate change over 30 years or longer. 50 years or longer is even better. So in fact, these ups and downs here represent climate variability, not climate change. Climate change is the long-term trend, the 30-year plus trend. And you're looking from here to here, that's called climate change. These zigs and zags here, that's climate variability. People who, climate change deniers will often say, hey, look, global warming is over. It's cooling here. Oh, look, global warming is over. Oh, look, global warming is over. But in fact, what you really need to look at is the long-term trend here. Now, I'm going to show you an animation of one of these records. In fact, I'm going to show you an animation of the NASA product, which is the one here. But all the other products would look pretty much the same, because look how close the agreement is between these. The agreement is quite good. That's what you want to see in science, and that's because we have lots of data to assess climate with. So what we're going to be looking at is an animation of surface temperature anomaly from 1880 to 2018. Now, anomaly is just a fancy way of saying temperature difference. Surface temperature anomaly is surface temperature difference from a reference field. And in fact, the reference field we're using here is the 30-year average from 1951 to 1980. And the temperature scale is shown over here, where it's shown to be white. That means it's the same value as that 30-year reference field. Where it's yellow to orange, it's warmer, and the dark oranges here are 2 degrees C warmer. Where it's blue to dark blue, it's cooler, and the dark blues are 2 degrees C cooler here. A couple things about this data record. It's only in situ data. If you're worried about computer models, forget it. There's no computer models here. No satellite data here. Satellite data can be tricky, but it's not used here. It's only in situ data. And it's a lot of data over the land. It's a couple of billion observations over this 100-year period. Over the ocean, it's about 450 million observations. You might have heard about the urban heat island effect. That's a real effect where all the the buildings and the concrete in a city will make the temperature anomalously warm there. Don't worry about it. Urban heat island effect stations have been taken out. About 200 stations have been removed from this analysis, so no urban heat island effect here. If you're a real aficionado of this business, you might be aware of the fact that at about the middle of the 20th century, there was a change in how ships made observations of sea surface temperature from bucket temperatures, where they actually threw a bucket over the side and reeled it back in on a rope and stuck a thermometer in there, to engine injection temperatures, where they measure the temperature where the seawater was injected to cool the engines. Well, there was a bias there. The bucket temperature bias cooled by about a tenth of a degree, and the engine intake temperature is biased warm by about 2/10 of a degree. That's all been corrected out here. Don't worry about that. It's all been corrected out. Now, I'm going to roll this animation, and I'm going to call out the decades. And you keep your attention focused on the color here and see what's going on. And pay particular attention to when we get to the 1970s, because that's where things really take off. So here we go. Okay, we're in the 1880s, 1900s, 1910s, 1920s, 1930s, 1940s, 1950s, 1960s, 1970s, 1980s, 1990s, 2000s, 2010s. Now we end up at 2018. So a couple of things about this. First of all, the land is warming faster than the sea. You can see, in fact, the land is warming about twice as fast as the sea, but the sea is definitely warming. You see all these yellows here. Even though about 95% of the heat of global warming is going into the ocean rather than the land, but the ocean's warming much less. That's because the ocean has about 100 times the heat capacity of the land. So there's a lot of heat being stored in the ocean, and it can store a lot of heat and not warm up that much. In terms of the land, as you go farther north, the warming gets greater. In fact, the greatest warming is happening in the Arctic region. That's not a good thing, because that's where there's a lot of ice, particularly the Greenland ice shelf here. And ice is melting, and that's contributing to sea level rise. We'll talk about that in more detail later on. It's not warming everywhere. Notice there are these patches of blue where things are cooling. And that's why I talk about global warming as a global phenomenon. You really need to look at the global record. You can find areas where it's actually been cooling. Generally, places where it's cooling have to do with changes in ocean circulation. So for example, here, the Gulf Stream has weakened and it's moved farther offshore over the last 100 years, and that's produced this cooling here. There have been changes in the Antarctic circumpolar current down here that have produced this cooling down here. And notice there are variations here. Where we live in the continental United States, notice that the Western United States has warmed quite a bit more than the Central or the Eastern United States. And of course, we've experienced that in terms of warming and drought and those kinds of things. So it's very non-uniform around here. And it's kind of important to keep this picture in mind. So what's going on here? What's causing this? Well, in fact, it is the greenhouse effect. And to understand the greenhouse effect, we really need to take a look at the Earth's annual mean energy budget, which looks like this. And what we're tracking here is incoming solar radiation. These numbers are watts per square meter, watts of flux of heat per square meter. Incoming solar radiation, some gets reflected by clouds, some gets reflected by the surface, goes back out to space, some is absorbed here. Then the Earth is cooled by outgoing long wave radiation or infrared radiation from the tops of clouds, from the atmosphere itself, from the surface of the Earth. So a question that may come to your mind is, what about other sources of heat? For example, we know that the Earth's interior is hot, and there's a flux of heat from the center of the Earth to the surface of the Earth. In fact, that's how geothermal energy works. So why is that on here? Well, heat from the Earth's interior is about 4,000 times smaller than the incoming solar radiation. In fact, all of the other sources of heat you can think of are negligibly small compared to the numbers in the data that's presented on this chart here. For example, waste heat from factories and buildings, transportation, et cetera. It's about 11,000 times smaller than the incoming solar radiation. The tides, the tides are running around the oceans every day, and there's frictional heating caused by that. It's called tidal friction. It's about 50,000 times smaller than the incoming solar radiation. So the bottom line here is that the heat fluxes, the flows of heat depicted on this chart really are the ballgame. They determine whether the Earth is going to warm up or cool down. They absolutely do. The other sources of heat are negligibly small. What really counts is three numbers. It's the incoming solar radiation, the reflected solar radiation going back out to space, and the outgoing long wave radiation or infrared radiation. Those three numbers are what, the sum of those three numbers are what determine whether the Earth is warming up or cooling down and how the climate is changing. And in fact, if you add these three numbers together, you get this number right down here, which is the net heat absorbed by the Earth. So with this picture in mind and understanding that this really is the ball game, other sources of heat are not important, the greenhouse effect looks like this. The Earth is warmed by incoming solar radiation, and it's cooled by reflected solar radiation and outgoing long wave radiation. Greenhouse gases trap the outgoing long wave radiation and warm the lower atmosphere and the surface of the Earth. And those greenhouse gases are water vapor, which we perceive as humidity, CO2, carbon dioxide, methane, nitrous oxide, and the F gases, a whole class of man-made gases that they're called fluorinated gases. And then finally, human activities increase greenhouse gases in the atmosphere and increase the warming. It's kind of like, you go to sleep at night, you want a blanket. And in fact, it's important that we have this greenhouse blanket here, because if suddenly you had a magic wand and you could make these greenhouse gases go away or make it so they didn't trap the outgoing long wave radiation, we would go into an ice age pretty quickly. Probably within 10 years or so, Monterey would be under an ice sheet about probably a couple 100 meters thick. So it's good that we have these greenhouse gases. It's kind of like when you go to bed at night, you want a blanket over yourself to go to bed. But what happens if somebody keeps, over the course of the night, they keep piling more blankets on, blanket after blanket after blanket, and it keeps getting thicker? Well, you start getting too warm, uncomfortably warm. And that's what's happening. In fact, humans are putting large amounts of these greenhouse gases, CO2, methane, nitrous oxide, and fluorinated gases into the atmosphere. Notice that I've colored water vapor differently. Water vapor actually traps more outgoing long wave radiation than any other greenhouse gas. So it contributes more to keeping the Earth warm than any other greenhouse gas. But I've colored it differently here because it is not driving global warming. It's participating in global warming. It's amplifying global warming through that water vapor feedback loop we talked about a little while ago. But it's not driving global warming. And the reason is water vapor is in balance with the natural hydrologic cycle, whereas these other gases are not in balance with any cycle, any natural cycle. And in fact, they're going up as we put more of them into the atmosphere. Also, the residency time for water vapor in the atmosphere is very low. You put a large amount of water vapor in the atmosphere, things are out of balance. What happens? Well, it just rains back out, and it happens within a matter of days. You put a large amount of CO2 in the atmosphere, it's going to be there for at least a century, and some will still be there after 1,000 years. Methane is also long-lived. So that's why water vapor is separated out here. It's not an anthropogenic greenhouse gas. Now, the warming is amplified by that snow ice feedback we talked about before. Increasing global temperatures yields decreasing snow and ice, increasing sunlight absorbed by land and sea. You can kind of see that picture here. A lot of the sunlight reflects off the ice, but when the ice melts, it's absorbed in the dark ocean. That warms things more, and that amplifies the warming. Water vapor feedback. As the oceans warm, and we saw in that animation how the oceans are warming, there's more evaporation that puts more water vapor into the atmosphere, and that traps more heat, that amplifies the warming. That's the water vapor feedback. Now, I know what you're thinking, because I know you folks are sharp, and I know what you're thinking. You're thinking, well, this must be an unstable system if we have only these positive feedbacks here. It's like trying to balance, you've got an ice pick, you're trying to balance it on the tip there. Well, you can never do that, because once it starts to nudge just slightly over, there's that gravitational feedback effect, and it just tips all the way over. It must be an unstable system. Well, it isn't. It's actually a very stable system, because there's a positive negative. There's a very powerful negative feedback, and that's the long wave radiative feedback. Now, this is the only equation I'm going to show you in this talk, so don't get mad at me. And this is actually based on a famous equation. It's called the Stefan-Boltzmann law. And it says that the outgoing long wave radiation that cools the Earth is actually proportional to the temperature of the Earth's surface in degrees Kelvin to the fourth power. Degrees Kelvin is just like degrees centigrade, except zero is at absolute zero, which is minus 273 degrees centigrade. And because of this temperature to the fourth power here, it doesn't take much of a change in temperature for this outgoing long wave radiation to increase rapidly. So as the Earth starts to warm up, because of this effect here, the outgoing long wave radiation tries to increase and cool the Earth back down. Works the other way too. As the Earth cools back down, the outgoing long wave radiation, because of this temperature to the fourth relationship here, reduces rapidly. It tries to warm the Earth back up. So if left to its own devices, the Earth would be the climate would be stable, and the system would come into equilibrium, and we would have a stable climate. The problem is we keep nudging it out of equilibrium by putting more and more greenhouse gases into the atmosphere. We keep nudging it out of equilibrium. The Earth is trying to catch up and get back in equilibrium. The way it does that is warming up, and the long wave radiation feedback is not powerful enough to keep the Earth from continuing to warm. So that's what's going on there. Now, this is not just me saying this. It's important for you to understand. I'm not telling you anything that just my theory. I'm basically presenting the settled science that is supported by all the leading science organizations around the world that have confirmed human-induced global warming. And here's just a partial list. It includes the most prestigious science organizations in the US, the US National Academy of Sciences, the US National Research Council, American Association for the Advancement of Science. It includes the two organizations that have purview over the atmosphere and the ocean in the US. That's the American Meteorological Society and American Geophysical Union. I could go down the list. There is an overwhelming international scientific consensus on this matter. There's really no doubt about that. The science is settled, and in fact has been for that. So let's talk about these greenhouse gases. And again, that's water vapor, carbon dioxide, methane, nitrous oxide, and the fluorinated gases. In terms of the contribution of these greenhouse gases to the current rate of global warming, it looks like this. CO2 is the dominant greenhouse gas. It's driving about 72% of the global warming we are experiencing, followed by methane, which is also known as natural gas, 20%. Nitrous oxide, which mainly is coming from agriculture, from fertilizers, about 5%. And finally, the fluorinated gases, the F gas is about 2%. Fluorinated gases are man-made gases. They're used mainly in refrigeration. They're also used in semiconductor production. They're also used as gaseous insulators and transformers and electrical connectors and things like that. So CO2 is the dominant contributor to the current rate of warming. So that's why we focus a lot of attention on CO2. And here's a plot of CO2 in the atmosphere from 1700 to 2019. And what you see is pretty stable up to a point of right about here, about the beginning of the 20th century. That's when we started burning coal. That's when we started, the Industrial Revolution really got going. Really took off in the 1960s. You may hear the term Keeling curve. That refers to an oceanographer, Charles Keeling, right down at Scripps Institution of Oceanography in La Jolla. He was the first to make very detailed measurements of CO2 in the atmosphere. The current CO2 is often reported in parts per million. The pre-industrial level was about 280 parts per million. We're now well over 400 parts per million. That's an increase of about 50% over the pre-industrial level. But it's also instructive to think about the mass of CO2 put into the atmosphere. From 1850 to 2018, human activities have put about 2 trillion tons, not billion, trillion, 2 trillion tons of CO2 in the atmosphere. and about 1.1 trillion tons are still there. And the current rate of CO2 emission into the atmosphere, as a result of human activities is about 40 billion tons per year. So where does all that CO2 go? Well, about 30% of it goes into the land, and it gets sequestered into the roots, into the soil through the roots of trees and plants, and that's a good thing. That's what we really want. That's part of the natural carbon cycle. About 20% gets dissolved in the ocean, and that's not so good because that's contributing to ocean acidification. The oceans are trending more towards the acidic side of the scale, and that causes problems for lots of marine life. And finally, the remaining 50% is accumulating in the atmosphere. So we're basically putting CO2 into the atmosphere about 2 to 3 times faster than the natural carbon cycle can take it out. And as a result, CO2 is going up dramatically, as you see here. So where's that CO2 coming from? Well, globally, actually, this is all greenhouse gases. Globally, by economic sector, it looks like this. The top three account for about 2/3 of all the greenhouse gases. Number one is electricity and heat production. That's energizing the power grid. Number two is agriculture, forestry, and other land use. That would be particularly livestock farming and also deforestation. And finally, number three is industrial production, particularly steel and cement production. Those three sectors account for about 2/3 of all of that. Transportation is next on the list and actually pretty far down. It's only about 14%. Now, this is globally. In the US, it would be higher because we drive cars a lot more. This is fossil fuel production, that's petroleum refineries. And finally, 6% would be on-site fossil fuel burning in buildings and homes. That would be heating and cooking with natural gas, for example. In terms of who are the big emitters, China is number one by a pretty wide margin, about 10 billion tons per year coming, which is about a fourth of the global, global emissions are coming from China. US is number two, down by a factor of about 2, followed by all countries of the European Union, India, Russia, Japan, and then on down the list. Now that's one way of looking at it, total CO2 emissions. Another way of looking at it is per capita. You just take the total emissions for a country, divide by the number of people in the country. Well, there's a lot of people in China, so they drop way down. The United States then becomes number one. We were number two over here, we're number one over here. The average carbon footprint for the average American is about 17 tons per year. The average American is putting about 17 tons of CO2 into the atmosphere per year. We're number one. But Canada, Saudi Arabia, and Australia are also pretty high. They're pretty close behind us. By the way, there's a good news story here for California. The average for the US is 17 tons per year. The average for California is about 11 tons per year. So we're doing pretty well. I'd like to say that's because we're green and we're progressive and so forth, and that's certainly part of it. But we don't have the big smokestack industries like other states have, and of course we have very mild weather compared to other states. So, but the bottom line is we're down. Actually, and there's another way of looking at it for California, which I think is a good news story. California produces about 3% of global GDP. We're the 8th largest economy in the world. Produces about 3% of global GDP, but only about 1% of global emissions. So that's a pretty good story. I think we're doing pretty well compared to the rest of the world. So we've seen where we are. We're about 1.2 degrees C above pre-industrial. Where are we going? Well, I like to show where we're going in the context of where we've been. So I'm going back to the 22,000 year look here. So again, we're looking at global mean surface temperature of the Earth from the present time back to 22,000 years ago. Again, here's where human civilization began right there. And here's where we are right now. Where are we going? Well, it depends on what we do. If we adopt the Paris Climate Accord, and if the country, if the world meets the goals of the Paris Climate Accord, all the countries play and they meet their targets, then the projection is we will hold global warming by the end of the century, by the year 2100, to 1.5 degrees centigrade plus or minus 0.7 degrees centigrade, which would put us right about here. And that's still pretty extreme. You think about it, think how stable things have been over the course of human civilization. All of a sudden we're going there. If we At the other end of the scale, if we reject the Paris Accord, continue on as business as usual greenhouse gas emissions, which means we completely ignore any efforts to try to constrain emissions. At the worst case scenario, we're not going to do that bad, but that's kind of one end of the spectrum. Then we're going up here, 4.5C plus or minus 1C. It's way up here, way up here. Now look how extreme that is. Compare, I mean, that's almost the difference between an ice age and a warm period. And the question on the table, the question is so concerning to many people is, can human civilization adapt to climate change this rapid? We've had a very stable climate over the course of the last 9,000 years, and now suddenly it's going like that. Now, I don't think we're going to go up here. I think we're going to come somewhere in the middle. I don't think we're going to meet the Paris Accord goals. We're certainly falling behind them now. We're definitely not on track. But we're doing better than up here. So we're going to probably fall somewhere in the middle. Even if we split the difference, that's pretty extreme, as you can see from this chart. So what are the global consequences of that extreme warming? Well, I'd like to divide them into two categories, natural consequences and human consequences. Natural consequences are increasing temperature of the land, ocean, and lower troposphere. And what do I mean by troposphere? Well, take a look at this diagram here, which is the schematic structure of the vertical structure of the atmosphere. And there are these layers of the atmosphere. The troposphere is the lowest layer here. That's where all the weather is. It's from the surface up to about, up to about 9 miles, 8 or 9 miles. Here's where you're flying in a jet airplane, and the pilot says we're going to fly above the weather. They go a little bit higher here to get above the troposphere. And what's happening with global warming is, it's important to know, is that the warming is actually occurring down here in the lower half of the troposphere. It's not occurring through the entire atmosphere. It's being trapped way down here. And in fact, the upper part of the atmosphere is cooling. In fact, the upper half of the troposphere is cooling, and everywhere above is cooling while it's warming down here. Why is that? Well, it's because the heat that would normally warm this part of the atmosphere is being trapped below. The problem with that is heating the atmosphere from below and cooling it from above makes it more unstable, because what drives weather, in fact, is warm air rising into cooler air. And you're making the atmosphere more unstable by heating from below, cooling from above. Also, the atmosphere is getting more humid. As the oceans warm, there's more evaporation, so the atmosphere is getting more humid. And that evaporation, or the condensation of water in clouds, helps drive the weather. And so it's making, again, the atmosphere more unstable. And these changes fuel increasingly strong storms and severe weather, which we can see in this diagram here. What we're looking at is the global number of severe weather events by year for 1980 through 2100. So this is just number of events, 1980 to 2010. Severe storms in green, that would be hurricanes, tornadoes, severe winter storms, severe floods, and heat waves, droughts, and wildfires, very topical for us, in the yellow here. And you can see there's been a clear upward trend over the last 30 years or so. So increasing floods, droughts, all those kinds of things, decreasing mountain snowpacks and earlier snow melt, which is a big factor here in California, since we get a lot of our water from the Sierra snowpack. Melting of ice sheets and glaciers, producing rising sea levels, decreasing pH of seawater, ocean acidification, decreasing the oxygen level in the ocean, increasing mortality of coral reefs due to coral bleaching, or it's referred to as coral bleaching. That's caused by the combination of ocean acidification and warming oceans, decreasing productivity of fisheries, and increasing species migration and extinctions with loss of biodiversity. Now, I want to talk a little bit about sea level rise. Being a Point Lobos docent, I bet you get questions about sea level rise from people. So let's talk about sea level rise. This is a depiction of sea level from 1900 to 2015. And you can see, and the blue part here is produced by tide gauges. These are gauges that measure, the water level, frequently, and then you average over periods of time. You can average out the tides and get the increase in sea level. There's a tide gauge on the wharf in Monterey, for example. The record here is actually produced by satellite altimetry. There are these satellites that can actually measure sea level from space, and very accurately. What we see is from 1900 to 2015, there's been a rise in global sea level of about 8 inches. And the thing that's also concerning here is that if you see, look at this curve, it's accelerating. It's accelerating and accelerating pretty rapidly. The increase in sea level here was happening much faster than it was back in the early part of the 20th century. So we'll talk about sea level in a little more detail later on in terms of local impacts. I just wanted to show that picture. So what are the human consequences of a warming world? Well, increasing economic costs resulting from increasing frequency and intensity of damaging weather events, increasing prevalence of wildfires, don't we know that, and rising sea levels, increasing competition among nations for water and food caused by increasing drought and decreasing agricultural and fisheries production, increasing displacements of people and unrest in populations susceptible to recruitment by violent extremist groups caused by increasing drought, floods, extreme weather, and sea level rise. Basically, climate change puts pressure on food, water, and living space. And there are lots of people in the world who are challenged in those areas. For example, Bangladesh. Bangladesh is a very heavily populated country. A 1 meter rise in sea level, it's been calculated, which is about what we're expecting by the end of the century, by the way. A 1 meter rise in sea level will displace about 30 million people in Bangladesh. They'll have no place to live. Now, where are they going? Well, they're not going to India. There's a wall there, and India's that will not accept them. They're probably not going to Myanmar. Where are they going to go? It's going to be a tremendous humanitarian crisis there. Generally speaking, a 1 meter rise in sea level will displace about 100 million people globally. A 2 meter rise will displace about 200 million people globally. So those are significant issues. Increasing mortality from heat waves, other severe weather events, starvation, disease, and war. By the way, heat waves kill more people every year than any other weather phenomenon. Hurricanes, tornadoes, forget about it. Heat waves kill more people than anything else globally. Heat waves are increasing. And finally, increasing threats to human health as tropical diseases spread into higher latitudes. Zika virus is a great example of that. Dengue fever is a great example of that. And reduced biodiversity, which increases the likelihood that diseases will jump from animals to humans. And there's been lots of examples of that. The coronavirus may in fact be an example of that. So what about the local consequences? That's what we can expect globally. What can we expect here in California? Well, California has been funding about every 2 years climate assessment studies. The fourth climate change assessment was done in 2018, done by Scripps Institution of Oceanography in La Jolla. And what I'm going to be showing you is taken from this report. And what we can expect is, of course, warming, continued warming. What we're looking at here, and first of all, where did this come from? Well, this was a modeling study. It was using an ensemble of models, which means a group of models. In fact, about 20 or 30 computer models that were produced and run by the IPCC, the Intergovernmental Panel on Climate Change, kind of the definitive organization in the world for talking about climate change. And there were some techniques employed. We won't go into to produce a more detailed view of where we're going by the end of the century. And in terms of temperature change, it looks like this. What we're looking at here is the change in annually average daytime high temperature in degrees centigrade, average over the last 30 years of this century, 2070 to 2100, relative to this 30-year average, 76 to 2005, for the worst case scenario, the business as usual global CO2 emissions case. Remember, we looked at it, had that big spike. So this is about as bad it could possibly get. I think we'll do better, but it's pretty bad. And you can see here in the Monterey Peninsula, we'd be expecting to warm by somewhere in the range of about 3.5 to 4 degrees centigrade. Multiply that times 1.8, and you've got degrees Fahrenheit. That's quite a bit of warming. Not as bad as inland. Fortunately, we're along the coast here, and that's going to help mitigate it because the ocean is cooling slower than the land, and it'll help mitigate. As you go inland, you can see the gradations here. It gets much warmer, but we can expect continued warming, and of course, that's the trend that we've seen. In fact, over the last 100 years or so, Monterey County has warmed. The globe has warmed about 1.2 degrees centigrade, but Monterey County has warmed about 1.9 degrees centigrade. So, the Western United States is definitely warming faster than other areas. That's the impact on temperature, but also an impact certainly on droughts. And again, from this modeling study using about 30 or 40 of the world's best climate models, what they found was that by the end of the century, under the business as usual scenario, which is the worst case scenario, we would expect severe droughts, which currently occur about once every 20 years, to occur about once every 10 years, about twice as frequently. And extreme droughts, which occur about once every 50 years, to occur about once every 25 years. Again, it happening about twice as fast and twice as frequently. And of course, those droughts will be exacerbated by reduced snowpack in the Sierras caused by reduction in proportionate precipitation falling as snow rather than rain. When rain falls, it just kind of runs off. We really want to have snow build up in the Sierra to get us through the dry season. And earlier and more complete snow melt. These more frequent droughts will place growing pressure on California water supplies and increasing prevalence of wildfires. This is the Oroville Reservoir. In normal conditions, the Oroville Reservoir in drought conditions, we're going to see it more frequently looking like that. Now, the other thing, of course, is sea level rise. And again, as Point Lobos docents, I'm sure you get a lot of questions about sea level rise. So let's talk about what causes sea level rise. And I'm breaking up into two categories here. Long-term, months to centuries, short-term, hours to days. Long-term, thermal expansion of the oceans. As the oceans are warming, the sea level is rising just because of the fact that the oceans are expanding. Warm water is less dense than cool water, so it expands as it warms. And in fact, most of the warming, or most of the sea level rise, I should say, in the first half of the 20th century was in fact driven by just simple thermal expansion of the oceans. The oceans warm, they expand, and it causes the sea level to rise. Next comes the melting of glaciers, beginning about the second half of the century, or the 20th century. The mountain glaciers started melting. And by the way, that's a great way to see the effect of climate change with your own eyes. Go visit a glacier. I've done it in Alaska, and you can see with your own eyes where the glacier is. There'll be a ranger station there. You can go in the ranger station. They'll have a picture, almost certainly, of what the glacier looked like 50 or 100 years ago. And you can see with your own eyes what the glacier looked like back then, what the glacier looks like right now. And you'll see that it's almost all of the glaciers in the world have, in fact, receded significantly. So that, of course, contributes to sea level rise, to the melting of ice and the water flowing into the ocean. Then finally, or I should say next, is melting of ice sheets. Now, there are three significant ice sheets in the world: the Greenland ice sheet, the East Antarctic ice sheet, and the West Antarctic ice sheet. In fact, most of the fresh water in the world by far is held in these ice sheets. Of course, the ice sheet is ice that exists over land. Extraction of groundwater. This is actually a relatively small effect, but it's not negligible. As agriculture goes on all around the world, there's pumping of groundwater, which then gets usually goes into agriculture, but through runoff and evaporation and precipitation, it eventually finds its way into the ocean, and that contributes about 5% or so to rising sea level. Changes in ocean thermal structure and ocean circulation can affect the sea level over scales of months to centuries. For example, when we have an El Nino, the sea level actually rises along the California coast. As long as the El Nino is in effect, it rises a few centimeters. Then, of course, at Point Lobos, you're observing all these short-term hours to days variations in sea level, which you see every time you're down there. There are the tides: neap tides, spring tides, Peruvian spring tides, and of course the famous king tides, the largest tides. Weather effects: wind, storm surge. When the wind is strong, the sea level rises. Atmospheric pressure is called the inverse barometer effect. When a low pressure system moves over us, the sea level actually will rise just from the pressure effect alone. Rainfall heavy rainfall will actually cause the sea level to rise briefly locally. And of course, surf from a distant source, huge waves coming in, will cause the sea level to rise. So these are all the things that affect sea level in the short term, in the long term, in the short term on the central coast of California. So where are we going? Well, again, under business as usual, worst case scenario, global CO2 emissions, sea level rise predicted for the Monterey Bay region, it looks like this. The upper row here is in centimeters. The lower row here is in inches. So if you want to think in inches, we'll look along here. Now, and these are relative to the 2000 mean sea level. So we had already risen about 8 inches from pre-industrial. So to convert these to pre-industrial sea level rise, you need to add about 8 inches to them. But in terms of sea level rise relative to recent memory, which would be the 2000 mean sea level, we're looking at about a 3-inch sea level rise by 2030, about 9 inches by 2050. And then look how things take off. By the end of this century, we're up to 53 inches here. Now this is, in the middle here is the most likely sea level rise. And the numbers here are the upper and lower bounds. They're the 90% confidence limits. So 90% likely that the sea level rise will fall in this range. It could be as high as 94.5 inches, as low as 28. There's a lot of uncertainty here, mainly because there's a lot of uncertainty about how fast the ice sheets are going to melt. What really drives this very rapid increase here is the fact that the melting of the ice sheets will accelerate, and we don't quite understand the physics that well to predict it that accurately, and so that's reflected in these large error bars here. So, not a pretty picture. What needs to be done? Well, I'm going to refer you to drawdown.org. It's called Project Drawdown. I'm a very strong fan of this group. Project Drawdown is a nonprofit organization that proposes, analyzes, and ranks solutions for reducing greenhouse gases in the atmosphere, with the goal of reaching drawdown, the point at time when the concentration of greenhouse gases begins to decline on a year-to-year basis. It was founded in 2014 by Paul Hawken. It presents 80 solutions for reducing greenhouse gases by avoiding emissions and or by sequestering carbon dioxide already in the atmosphere. The solutions consist of technologies, practices, and policies organized into 9 sectors and implemented in 2 scenarios. And I strongly recommend you visit their website. It's really excellent. You can spend a lot of time there. We don't have time to go into much detail on it, but it's very well done, and you can really take a look at it. It essentially provides a roadmap for stopping and eventually reversing global warming and climate change. So I just want to touch on it briefly. Here are the 9 project drawdown sectors. It's electricity, food and agriculture, land use, industry, transportation, buildings, health and education, land sinks, coastal and ocean sinks, engineered sinks. So electricity is pretty straightforward. You know, you're talking about rooftop solar and, wind turbines. Food, we want to try to get away from heavy beef-oriented diet. Beef is very greenhouse gas intensive. The rest of the world is trying to shift to a diet like ours, and that's not a good thing. We're trying to get away from that. Trying to do agriculture more smartly. Industry, make it more efficient, get away from the heavy use of emissions there, make transportation more efficient, buildings more efficient. Health and education really is oriented towards trying to hold down birth rates. We're about 7 billion people in the world now. There's projections we could go to 11 billion by the year 2100. Every soul coming into the world brings with them a carbon footprint. So we want to try to really hold down population growth. Land sinks has a lot to do with stopping deforestation, planting trees, that sort of thing. So you could spend days looking here, but if you really want to get smart on this and really dig into what's out there that can help us address this problem, take a look at drawdown.org. Now, the other great thing about Drawdown is they have very carefully costed out these solutions. They've costed them out in terms of what investment is required and how much greenhouse gas the different solutions sequester. And they've ranked them, and they've costed them out. They've even done analysis of how much savings there are. They have economists on their staff, scientists and economists, and they've really done a great job here. They've analyzed things in 2 scenarios. They're key to the Paris Accord. Scenario 1 is hold global warming to 2 degrees centigrade, which is the basic Paris Accord. Scenario 2, the basic Paris goal. Scenario 2 is hold global warming to 1.5 degrees C, which is kind of the stretch goal for the Paris Accord. So they've costed it out. And the 30-year cost to the world to achieve scenario 1 is about $23 trillion over that 30-year period, which amounts to about 1% of global GDP, which is, it seems like it's doable. To get to 1.5 degrees centigrade, Holding it to that level would require about 1.25% global GDP invested up front over the next 30 years between now and 2050. The good news here is there's a cost savings. Over that 30-year period, the 30-year cost savings overall would amount to about 95 trillion in scenario one, and actually about 145 trillion in scenario two. Now, if you apportion those costs out to all the countries of the world in proportion to their GDP, then the cost of the US for scenario one would be about 190 billion per year, every year for 30 years. For scenario two, about 250 billion per year, every year for 30 years. For point of reference, the defense budget is about $1 trillion per year. So we're talking about, maybe a quarter of the defense budget. And there's savings here, about 780 billion per year saved here, and about 1.2 billion per year saved here. Now, no illusions here, not easy to find 190 billion per year in the budget. But also this doesn't have to all be government investment. Lots of private industry investment would go here too. For example, in wind turbines, there's lots of private companies that are investing in wind turbines. But the other thing is, according to the International Monetary Fund, the global fossil fuel industry is currently subsidized at about 5.2 trillion per year, or about 6.5% of global GDP per year, which is way more than we need to invest here. According to the IMF, the US fossil fuel industry is currently subsidized at about 650 billion per year, which is way more than we need to invest. So there's money there if we were to start drawing down these subsidies to the fossil fuel industry. In fact, we wouldn't have to take them to zero. We just take them down by a factor of 2. We'd have plenty of money to invest here. Now, no illusions, that would not be easy to do. Well, actually, the first question is, why are we subsidizing the fossil fuel industry? And how do we do it? Well, we do it through tax breaks that are heavily and deeply embedded into the tax code. Why do they ever get there in the first place? Fossil fuel companies are the richest companies in the world. Well, think back to the 70s when we had the oil crisis and we were being held hostage by Saudi Arabia and we had not a lot of production. There was a strong emphasis to make the United States energy independent. And the way we pursued that was really stimulating the fossil fuel industry in the US through these tax subsidies and these tax breaks. And it worked. We are now a net energy exporter, but the tax breaks are still there and they're deeply embedded in the code. They are protected by an army of lobbyists. They're protected by members of Congress who are heavily funded by the fossil fuel industry. So I'm not saying it'd be easy to get them out, but ultimately that's kind of the direction we need to go, in my opinion. So I'm going to end up with some closing comments here. What actions can you take as an individual? Well, first of all, you can learn the basics of the science behind why our planet is warming and the climate is changing. And you've taken a huge step today by suffering through my talk. And I'm sharing the slides with you so you can take a look at them later on if you want to dig a little more deeper into it. You can do what you can to reduce your carbon footprint while living the life you want to live. You can join an advocacy group such as the Citizens Climate Lobby and participate actively. Whenever you have an opportunity to interact with a leader in your community, be they political or otherwise, let them know that you want to see action taken on this issue. You can become a leader in your community on this issue. I know many of you already are. And finally, vote for candidates who will address your concerns about climate change. Okay, that's it. And I know I've gone on a little bit long here, but hopefully we have some time for questions and a little discussion.
Mike, I would agree with you. We have gone long, but I think people appreciate it. I do have a couple of questions. I'm going to unmute Castel. Do you have a question, Castel?
Yes. First, Mike, thank you very much. That was extremely informative.
Thanks.
I think we all know people who are climate change deniers, and I think a big part of the process is going to get people to accept that. I've tried talking to people about dissolved gases in ice core samples just to try to get them aware that the problem has been going on. That there are numbers that we can point to to highlight that there is, in fact, human-caused climate change. And I've had very limited success with that. And I was wondering if you had maybe an elevator speech that you use on people or try to reason with people to convince them that there is indeed human-caused climate change.
Well, I have limited success there, and my patients often wear thin. I tend to talk about international global, international, overwhelming scientific consensus, and I show, all these organizations that have gone, I talk about 97% of the scientists in the world agree with global warming. And usually I end up saying, um, there's a Nobel Prize out there waiting for someone who can overturn this international consensus. So if you think you know better than all these scientists in the world and all these organizations, write up your results, send them off to a journal, and prepare to accept your Nobel Prize. Because if you can overturn the consensus that's out there, then certainly you'll be deserving of such a prize. It doesn't work.
Thank you.
It makes me feel better.
In deference to time, I'm going to go with one more question. I've unmuted George St. Clair.
Hi, Mike. Thanks so much for all the work you do, the essential work you do.
Thank you.
And for this presentation. I hope, is this a similar presentation available on YouTube, for example, that we could easily share with others outside of Point Lobos docents?
Yeah, I do actually have a YouTube channel. It's called Climate Change Matters with Mike Clancy. So you can just go on YouTube and search for that.
Okay.
Yeah, Climate Change Matters with Mike Clancy. And I've also shared my slides with Don, and I think he's going to share them with everyone. So, and it has the title of that YouTube channel there. And there's a number of different talks there. And each one has kind of a little bit of different focus, but you'll see a lot of overlap with what I presented today.
Yeah, it was so rich, a very rich presentation. Just what I was looking for.
Great.
A question that just occurred to me.
Yes.
So rising CO2 should increase photosynthesis by land and marine plants, right?
Yes.
So to what extent does that mitigate the threat, the impact of increasing atmospheric CO2?
Yeah, a little bit, but not enough to keep up with the rate at which we're putting it into the atmosphere. We're putting CO2 in the atmosphere about 2 to 3 times faster than the natural carbon cycle can take it out, including the part you're talking about right there. And so to get where we need to be, to achieve the 1.5 degree C Paris Accord goal for the end of the century, we need to get to carbon neutral by 2050, which means we need to reduce our emissions by a factor of about 2 to 3 by 2050. And we need to keep reducing from there. By the end of the century, we need to be pretty close to zero. Not exact. We're never going to get exactly to zero, but we can get pretty close to zero in terms of emissions. And unfortunately, we're falling behind. We're not meeting those Paris Accord goals right now.
But setting aside more areas on the Earth, on the globe, for vegetation would certainly not hurt, right?
That's a big part of it. There's a lot of talk about afforestation, which is planting forests where there was no forest before. And I just saw a recent presentation that there's actually about the size of the continental United States available in the world for forestation. But the unintended consequence there is, as you plant more trees in places like that, you're kind of starting to encroach on farmland, and you're starting to take land that could be turned into farmland out of potential farm production. At the same time, when our need for global food production is going to go up because population is increasing. So, there are trade-offs there that have to be played.
Yeah, thank you.
So, Mike, I would, on behalf of the whole organization, I would like to thank you. I have several requests here for the slides, and thank you for allowing us to make them available. I think I speak for everybody when I say the reason for everybody wanting the slides is it's hard to reconcile 40 billion tons of CO2 going into the per year. At the same time, we're talking about just the huge numbers associated with that. 10 billion tons in China, 5 billion tons in the United States. The huge numbers. At the same time, we're talking about a degree, 1.5 degrees, 0.9 degrees difference between what is being emitted and whatever, and to reconcile how we deal with those huge numbers and the small numbers, and understanding the difference, and the fact that, hey, if we're having global warming, how come I'm so cold, is sort of the thing. you've laid that out for us by doing a very nice job of step by step going through the whole issue. And I want to thank you, and I'm sure everybody else does. And I know your email and whatnot are on those slides, and don't be surprised if the 75, 80 people who are here all send you questions afterwards. So Betty, I'll let you end this, and thanks again, Mike.
Okay, thanks again, Don. Thanks again, Carol, for setting this up for me. And like I said, I'm a big fan of the Point Lobos Docents. Keep up your great work down there. And if you have additional questions, please do email me. I'd be happy to respond to you.
Yeah, I would echo your thanks to Carol for bringing you in here.
Okay, thank you very much. Bye-bye.
You're welcome.